So we are looking at the assumptions of regression. The other time, one of the guys asked the question, and I said, everything will be handled under the assumptions of regression, the properties of regression. What is an assumption? An assumption assumptions are certain things that must be in place for certain things to work. So, for example, you cannot assume that the university is running, or you cannot say the university is running. By the time you say the university is running, you have already assumed that lecturers are on campus, students are on campus, and things are ongoing. Yes, Marwin, that was a question. So you cannot assume that the university is running unless you have an assumption that the facilities are in place, students and lecturers are in place. So assumptions are certain things that must be in place for certain things to work. To undertake a regression, to establish an influence of some variables on some dependent variable, to establish causality or make prediction, certain things must be in place. And those are things we call the properties of ordinary least squares estimators. Sometimes we call it the classical linear regression model assumptions or axioms. So the first assumption is the zero mean of the error term. Now, what is the error term? The error term are certain factors that could also influence the dependent variable, but those factors have not been taken care of during the process of the modeling. So these error terms are very, very important. They are errors, they are noises. You don't see them, but behind the scenes, they are affecting the relationship between the dependent variable and the independent variable. They are influencing the relationship. So we are going to make an assumption that these error terms, their expected values must be zero. The word expected value means they are averages, they are mean. So the first assumption is that the mean of the error term, the average of the error term must be zero. Remember, when you have the regression line and you have some points above the line and some points below the line, the point below the line will carry a negative error. The points above the line will carry a positive error. The average of these errors should be zero. So the negative and the positive must simplify to an average of zero. Okay, now this is known as weak exogeneity. But when we get to panel data later on, you will notice that there is a strict exogeneity. In a panel data, we are looking at not just an error of an individual I, but we are looking at the error of an individual I over time. So time matters here in a panel data. But just understand for now that the error term, the mean of the error term must be zero. That's the main thing for the first assumption. Let's go to the second one. The second assumption is homoscedasticity of the error term. Remember, most of these things are about the error term. The homoscedasticity assumption says that the error variance must be constant. Okay, there must be constant variance of the error. Now, what do we mean? If I am looking at the relationship between X and Y, for example, and I look at this relationship, okay, if you just look at the relationship I've just scatter plotted here, and then you look at this second relationship, okay, I've scatter plotted some data between X and Y, and then look at this third relationship, okay, I've scatter plotted some data between X and then Y. My question to you is that, do you detect a pattern? Let's call it figure A, figure B, figure C. Do you detect a pattern in any of these figures? Who can tell me? Do you detect any pattern in these figures? Can you detect a pattern? You can tell me whether or not there is a pattern. Daniel.
Yes, for the first one, I can see a positive relationship between the S and Y. And then the second one, a negative relationship. The third one, I don't see any relationship at all.
Thank you. So the third one, there seems to be no pattern per se. Now, if this is about errors, if the axes have been changed and they were about errors, and you have the errors showing there, you will notice that there is no proper pattern in the last one. And that is known as heteroscedasticity. Once you are able to detect the variation is constant, there is a pattern. We are talking about homoscedasticity. So homoscedasticity, before you do a regression, before you undertake a regression modeling, the variance of the error given the independent variable must be constant. And so combining that assumption with the fact that the mean of the error should be 0, the first one, then you can say that the error, which sometimes we will also represent by epsilon, sometimes we'll represent it by UI, sometimes we represent it by something else. The error is should be independently and identically distributed with a 0 mean, normally distributed with a 0 mean, and then a constant variance. So this information here summarizes homoscedasticity and 0 mean of the error term. So the errors must be normally distributed, and the variance is the dispersion from the center of the error. The dispersion must be constant. So if you are doing a regression and you identify heteroscedasticity present, you have to correct that before you proceed. Because if you don't do that, you could have insignificant estimates. It will lead to a misleading conclusion that will come out of the regression. That is a second assumption. Now, the third assumption is still about the errors, but this time it is about an error of a particular observation and then the error of another observation. The last time, you can remember that we were trying to show different errors in the vector position or the matrix. We were showing, when we plotted them in the matrix, we show something like UI1, okay, or UI2, UI3, so each observation will have an error associated with it. So you have the dependent variable, okay, and then you have the independent variables, and then for each one, there will be some errors. Now, the no serial correlation or no autocorrelation of the errors says that an error with a particular individual observation should be orthogonal. In other words, it should not be correlated with the error of another observation. Because remember, the errors are already hidden. And so if the hidden is correlated with another hidden, that is a kind of a double correlation. And that is quite dangerous. So they must be independent of each other. That independence of the errors is what is known as the covariance of the errors must be 0. The covariation, that is the correlation, okay, after standardization, the correlation of the individual noise terms must be 0, which means there must be no interdependence between two different errors. This has to be satisfied. If it is not satisfied in the regression, you will have misleading conclusions. It will affect so many things we shall look at later. We'll later look at diagnostics and how to handle these things, how to detect them, and then how to handle them. Let's go to the next assumption. So we've spoken about three assumptions. And the next one is called zero covariance between the error and the independent variable. So you have a particular independent variable, let's say experience. Okay. Experience. You have a particular independent variable called experience. The experience of a person is affected by the ability of the person, which you don't see, is hidden inside a person. And that ability of the person is influencing the behavior or the experience of the person. You can have a special ability without even experience. But if you have experience and you have an ability, it's possible that your experience is being influenced by your ability. So if you're very good in doing something in particular, that will influence. If you have been in the army before, like this lady who acted woman, this lady, woman king or what, Iron Woman or something. That lady, she was in the army, and she's able to act action movies because of the training and the discipline and the ability that she has. So when she's able to come into the movie, she's able to shoot a lot of action movies because she's got an experience of body physique. Now, if that's special, she may have even a special ability, or acrobatic abilities and things, and that will influence that experience. Now, so you cannot disentangle the two. You wouldn't know whether it's the experience of the person making the person do this, or his ability within the person you don't see. So when there is a correlation, when the two are interdependent, when the two are dependent, well, like when your experience is dependent on your ability, that causes a problem of endogeneity. And that endogeneity can lead to a whole lot of troubles, resulting in misleading conclusion in a regression. The job of the Gauss-Markov, assumption is that there should be no endogeneity. There should be complete zero covariance. There should be independence between what you don't see, the error term, and what you see, which is the independent variable. This is an important assumption, very, very important, and even more important when we come to panel data. We'll look at it deeply, as we go forward. Another assumption. The next assumption, the fifth assumption, is the regression assumes that the relationship between X and Y are linear. The relationship between X and Y are linear. Now look at this. I have Y here, and I have X here. The relationship between X and Y are linear. For example, if you have Y is equal to MX plus C, the relationship between Y and X is a linear relationship. If you increase X by a certain percentage, Y will increase by a certain percentage, and that continues like that. But if you have a relationship like Y is equal to X squared, in that case, the relationship is no longer linear, it is non-linear. It is quadratic. Okay, now, but pay attention here and note that the linearity assumption has to do with the parameters, the beta. So X can be non-linear. You can have log of X. You can take the log of the quantity demanded of gene betas. You can take the square of the quantity demanded of gene betas. You can even interact some of the variables, okay, between income and occupation and income and location. But the parameter, the relationship, has to do with the parameter. The relationship between Y and X must be linear in parameters, in the parameter. So the beta coefficient, okay, that you later find, the relationship between the y and the x via the beta coefficient has to be linear, even when the independent variables themselves are log linear or squared or polynomial or interactive. Linearity is very important. Sometimes if it's not linear, you can linearize it. And one way you linearize some of these things is by taking the log. We'll look at that as time goes on. Now let's look at the next assumption. The sixth assumption is that there must be no perfect multicollinearity. What is multicollinearity? Now let me take you back to the one that we were doing, the zero covariance. Remember, the zero covariance was between the u, the mu, and then the x. But the multicollinearity has to do with one x and another x. So all of them are independent variables. Multicollinearity exists when two independent variables are so highly correlated that it becomes difficult to disentangle the partial effects of one from the other on the dependent variable. I think I've given you this definition. Okay. So the independent variable, it's about independent variables, and these independent variables are so highly correlated, like experience and education. Experience and education are so highly correlated that you can't even tell which one is leading to the increase in salary. When you have such high multiple in the data set, you have to handle it. When we come to diagnostics, we'll diagnose it and handle it using something we call variance inflation factor. But when you have a lot of multicollinearity in the data, then your best choice would be to use a ridge regression instead of going to use ordinary least squares. Ridge regression is a typical example of a machine learning algorithm that one can use. I'll show you this in the process. But you can still use the ordinary least squares and still correct for the multicollinearity. And we shall do that as well. So we've looked at 6 assumptions of regression. There are some other basic ones. Well, they are not that too basic. The other is a misspecification or specification bias. If you are supposed to correctly specify a model, and that model you wrongly specify it, for example, size of a company. The size of the company can be measured by the total assets of the company. If you have the total assets of the company, that total asset of the company can define the size of the company. Suppose you introduce this into the regression model, just as it is. Okay, you may have caused a specification bias. Why? Because you have introduced it as indicative of a positive relationship or a linear relationship between that total asset and maybe profitability measured by return on assets. So the relationship between profitability measure and total assets is probably linear. That's what you would have introduced. But then the total asset may have to be squared. Why? Because as companies become larger, the size increases, that could cause problems. There could be diminishing marginal returns to growing. There are studies that have shown that too big can cause some problems. Mega measures can lead to problems. Why? Because there will be difficulty in monitoring employees' actions and behaviors, and there may be difficulty in coordination. The CEO can take a lift with an employee when he doesn't know the employee is working with him, because the company is too big to the extent that he doesn't even know his own employees. It can also lead to checking. Some people can lazy about. If you look at most of the public sectors, they are so big, so big that some people do absolutely nothing. They just get into their office late, they start reading the newspapers. By the time, by some few minutes, it's 12 o'clock, they have to go for lunch and just that. So there are so many square pegs in round hole because of mega sizes. So because the possibility of size exhibiting diminishing returns, it's important to take the square of the size in addition to the size. Introduce that. If you don't specify your model that way, you have run into a problem of specification bias. And regression assumes that there is no specification bias. So it means that if you have a specification bias, it could lead to insignificant outcomes and misleading results. The next one. So you are beginning to see that for regression to nicely work, certain things will have to be in place. We've looked at quite a good number of the assumptions of regression. Right. Now, before you do regression, it's important to understand some of these terminologies. This is a dependent variable, and it is influenced by some factors. Beta 1, x1, plus beta 2, x2, plus beta 3, x2 squared, plus beta 4, x1 times x2, plus beta 5, x3 or something, plus the error term. Now, suppose you have a kind of a regression like that. There are certain terminologies you need to understand very, very importantly. One of them is mediating variables and interacting variables. One of them is a logarithm. Why do you have to take the log, okay, of some of the variables? I could have just said log of, y. What are the reasons for taking squares of some variables? So let's start. First one. In some cases of your regression, you have to take the logarithm of some of the regressors, and sometimes even of the dependent variable, which is y here. Why? What will warrant such situation? Well, the thing is that the log of some of the regression will impose something we call constant percentage effect. Let's take, for example, nominal inflation. If x1 here is nominal inflation, if you do not take the log, you are going to use that nominal inflation to look at its effect on GDP. But it's important to purge the inflation or deflate that inflation from, possible nominal situations. It is important to get the real inflation. Why? For example, if you are given a salary of 5,000, that salary, 5,000, can buy certain things in Africa, but it will not buy certain things in Europe. It can buy certain things in America, but can't buy certain things in Ghana. Why? Because that amount is a nominal value. So if you translate that salary into real value, real salary, then you will take care of inflation. So you got to purge the nominal salary and change it into real salary. That is, you got to look at the purchasing power of the salary. So it's not like I've given you 20,000 and you're happy. How much can that 20,000 buy? What is the purchasing power behind that 20,000? Now, in order to introduce this real element into the data set, in order to do that, you may have to take the log of the variable. You get a point? When you take the log of the regressor, the possibility of it taking care of the nominal element is very, very high. So you want to handle some of the, but it doesn't mean that because of that, you will be you'll be taking the log of every variable. For you to do that, you need to support that with the literature. There must be a theoretical backing, an empirical backing, some methodological backing that says that this variable, you got to take the log. Yes, Felix.
Okay, Prof. Is it that when the other variables, like in the case in the GDP, is it when it is it's real GDP or when it's nominal that you log the inflation to, so that, I don't know if you get the question.
Yeah, if the GDP is real GDP, you are not taking the log. But if the GDP is also nominal GDP, you have to take the log of that and take the log of the nominal inflation. But the thing is that if any one of them is already real value, you don't need to take the log again.
Thank you, Prof.
Yeah, the log that you take must be supported by the literature. Okay, apart from taking the log, and whenever you take the log, then you change the way you interpret the results. Please note, we'll look at that later. But the way you interpret the result change to percentages instead of, you know, normal thing. For example, you will no longer be saying that a $1 increase in something will lead to this blah blah blah, but it becomes a 100% or 70% increase in days will lead to 20%. So the way you interpret the information is now in percentages when you take the log. Sometimes you also have to take the square of some variables. For example, some independent variables. Why? I just told you the variable like this could be having a square. The variable is exhibiting non-linearity. A square means that it is showing some quadratic polynomials. So you got to capture that. Is that real? Yes, because some things actually are like this. They rise, they rise, they rise, they reach a point and then they start falling. Look at the experience of footballers. Sometimes the experience of footballers will rise, it keeps rising, it gets to a point. Then you get to a point, you realize the footballer is really no form. The form is coming down. That is exhibiting diminishing marginal returns. I know.
Yeah, Doc.
Yes.
So, Doc, what does it mean to say you log the regressors, to take the log? What does it mean, Doc, please?
Okay. So what it means is that suppose you have a particular variable, say salary, okay, and the salary is say 20, another is 50, another is 70, okay. You would take the log of 20, okay. So in the next section here, you create another column called the log of 20, the log of 50. Now, it will give you a different value, okay. Now, this value you are going to get, if you go to your calculator right now, okay, you will see this log. You take any calculator, okay, and type, for example, 100, and then go and then take the log of 100. Once you take the log of 100, it will tell you the value is 2. If you take, say, the log of, 400, okay, it's like 2.6. So what you're doing is that you are standardizing the value. You are moving it from factors that have influenced the value to look kind of inflated. And then your job is more or less bringing it into real sense, what it is really, for it to be used for policy purposes. Please, do you get it?
Yes, sir, Doc.
Okay.
Thank you
so
very
did you
much.
try it on your own calculator? You can see the log of some variables. Yes. If you try it, you will notice that that's how it is. So it means that you have to create a certain column. In R software, you can command it to do it automatically for you, and then you can further use it for further work. But just note that you may have to take the log of some regressors, take the square of some regressors, and each one you are doing must be supported by the literature. Okay, then there are some variables you have to interact, and there are some variables you have to mediate. These two terminologies can be very confusing, believe you me. Interacting variables and mediating variables. So let me just give you a couple of examples to appreciate it. When we talk about mediation, okay, as it sounds in the peace accord situations, mediation is an intervention. So when you are mediating, you are intervening. And it has to do with the causal sequence among 3 variables. So let's assume that you have this variable. Okay. You have a variable that is x. And you know that that variable X will affect the variable Y, it's influencing the variable Y. Let's say you have a variable that is, say, experience, which is X. And the experience is influencing a person's salary, which is the Y. But before the experience can influence the Y, there is a particular variable that you have not taken note of that the experience will affect before that variable will affect the Y. I'm just trying to think about a typical example with the example I've given. Okay? But you have to get a variable, and that variable is M. So the experience, X will affect the M first before the M will affect the Y. That variable in the middle is called a mediating variable. And so sometimes one will have to look at some, for example, if you want to measure the profit of a company, you want to measure the profit of a company and you say that the total assets, what do you call it? The total asset of the company can affect the profit of the company. But before that total asset can affect the profit of the company, the total asset itself will have to affect the return on assets of the company before the return on assets of the company is used as a proxy measure for the profitability. Okay, or let's look at shareholder value. You believe that total assets can affect shareholder value. Okay, shareholder value. But shareholder value itself, before it will be affected by the total asset must affect what is known as the profit of the company before the profit of the company will affect the shareholder value. So that profit of the company becomes a mediating variable. A mediating variable. Now, please know that a mediating variable is different from a moderating variable. A moderating variable is the same as an interacting variable. Moderating and interacting are the same. They all mean the same thing. What does it mean? It means that you are looking at the effect of the independent variable on the dependent variable, but then that is dependent. It's conditioned on the level of a third variable. So not that total asset affects profit and then profit affects shareholder value. No. But then total asset affect profit, affect shareholder value, but total asset itself depends on another variable before it can better affect the shareholder value. So there is a third variable, and that third variable is called interacting or moderating. Let me use a chart to demonstrate this very nicely for you, okay, so they can appreciate it better. So here you have an independent variable here, okay? And this independent variable is a workforce diversity. So in a company, the diversity of the workforce, okay, can go a long way to affect the effectiveness of the organization. If there is a lot of black and white in the company, that appears to give you an impression that this company is not a racist company. And so, you know, it could be something else. It could be the culture. It could be the way they all come to work. It could be the way they all work in teams together. There could be some workforce diversity. And that can bring about organizational effectiveness. Organizational effectiveness is the dependent variable. However, before the workforce diversity will affect the organizational effectiveness, it must affect the creativity of the organization. The creativity of the organization becomes the mediating variable. Because if it does not affect the creativity will not go ahead and then improve the organizational effectiveness. Creativity is a mediating, not a moderating, not an interacting variable, but it's a mediating variable. You need that creativity before finally workforce can affect organizational effectiveness. However, there are some variables you don't really need that before the workforce can affect the organizational effectiveness, but then they come to interact. When you interact them, when you combine them, with the workforce, it becomes good. For example, when you have workforce diversity and then you have managerial expertise, because of the managerial expertise added to the workforce, these together can beautifully, lead to organizational effectiveness. In this case, managerial expertise is a moderating variable. It's also a good variable on its own, but when you combine it, but then mediating variable, it has to pass through it before it can affect organizational effectiveness. Having said all that, there could be other factors that you have to control, and these factors are called control variables. The control variables may be completely different from all of these we are talking about because you are aware of them, you know them, and they can in themselves directly affect organizational effectiveness. So that is the difference between mediating and moderating. Moderating is the same as interacting. Okay? Mediating is intervening or intervention. So that is the difference between the two. Another example you can give is intelligence. Intelligence can lead to earning potential, which is a dependent variable. Intelligence can bring about earning potential. However, for intelligence to bring about earning potential, it would have to pass through some academic achievement. It would have to pass through some projects or business achievement. So until you don't just get up with intelligence and then you are able to get the potential for higher earning. No, because you're intelligent. Because you're intelligent. No. What your intelligence will have to do is that it has to pass through some business achievement, academic achievement. You got to use that intelligence to generate some value. Then your value will command its own earning potential. So that value, that academic achievement, which is a necessary, is a mediating variable between intelligence affecting earnings. But in the process, there could be a moderating variable. You don't just say that intelligence can affect earning potential, and so, it passes through academic achievements, which is a mediating, and that's it. No, sometimes you have to add effort. For example, imagine you are intelligent, but you are also hardworking physically. You are combining effort with your intelligence. So that becomes a moderating variable. It is making even your intelligence become much more beautiful, wonderful, powerful. Okay? And that is the beauty of a moderating variable. So ladies and gentlemen, I want to believe that you understand the difference between moderating, and mediating variable. Is very important to understand this because you are going to use the specimens of this. You're going to be giving some data sets for you to detect which ones are the moderating, which ones are the mediating, which ones are the control variables, which ones are the independent variables, which ones are the dependent variables, and then you are going to use the knowledge you've acquired here to be able to come out with such solution before you even run your data. All right. So that is it. Now, how do you do regression? The last time we were able to go through it, we said we have to generate some parameters and all of that. There's something you want to know about regression, and that is estimate and then estimator. What is the difference? The estimate and then the estimator. Who can tell me the difference? The difference between the estimate and then the estimator. Estimate and then estimator. Who is strong? Yes, Felix.
The estimate is the dependent variable, then the estimator is the independent variable.
Okay, Felix, you have to come again. You have to come again. Who is going to help Felix? Robert.
Yeah, Doc, I think the estimator is the approach that you use in determining the estimate.
That's
So
it.
yeah.
Continue.
Now saying the estimator is the approach used in determining the estimate. So at the end of the day, a value is estimated, or a variable is estimated. So the estimator is the approach. The estimated is actually a figure that has been estimated at the end of using the estimator approach.
Good. Who else has some addition? Who else? Yes, Martin.
Yes. That is used to estimate the betas.
Okay.
And the betas are the estimates that arise out of the estimators that are used.
Okay. So the estimator is like the rule, the recipe by which the data is transformed into an estimate. The estimator is the true parameter. Okay. The true parameter. After you have gone through the data and you have been able to, achieve whatever, then the value you get, the coefficient you get is the estimate. But that coefficient is just an estimate of a population parameter. It's an estimate of a population parameter. So the estimate is like a number, the estimator is like a letter. To get the parameter estimate, you need an estimator. The estimator is the process, the rule, the algorithms necessary to achieve the estimate. And there are several estimators that have been proposed in econometrics. One of them is the ordinary least squares regression. This was by Adrien Marie Legendre in 1805. The ordinary least squares is a very popular estimator. The other one is the maximum likelihood estimation by R.A. Fisher in 1922. The maximum likelihood estimation is very powerful because it's very good when you are dealing with classification data. The generalized least squares estimator by Alexander Aitken, and later on the feasible generalized least square, which is the applied version of the generalized least square, and it's also called a weighted least square. So all of these are the estimators. Guess what? We are going to look at all of them except the maximum likelihood estimation. So take note of this. Okay. The question becomes, when do you use which one? We shall look at them in the process. So let's start with a goal of regression. This is a little bit technical, but you should be able to follow me through. Please pay attention. The last time we were able to understand that this is a matrix. Okay. We have been able to convert the entire data frame into this, which is a matrix of Y columns and a matrix of multiple X columns and a matrix of the error time columns, the epsilon. This is a matrix. Our goal in OLS, ordinary least squares, is to minimize the error sum of squares and eventually come out with this beta. Okay. We are trying to find the beta hat, and we are using the estimator known as the OLS estimator. The cap or the hat on top of the beta simply means that we now know the value of that beta. How do you achieve the value? The values are known as coefficients in a regression. How do you get it? You need to have some bit of theoretical grounding. So that's what I'm trying to do, just for us to have some bit of theoretical grounding. So the first thing that you want to notice that this X bar x beta plus epsilon, and then you have y equal to all of that. If I decide to apply x prime to this data set, I have not done anything wrong with the data. The left-hand side will still be equal to the right-hand side. So I'm applying some x prime to every item in the data set. Your question might be, why are you doing that? Because our goal is to use that approach to be able to arrive at a beta estimate. What is x prime? Remember that x is a matrix. And therefore, x prime gives you the transpose of x. It gives you x being turned the other way around. So if x was in the form of a rows, you are now turning them into columns. Once you've done this, the next thing you can do, and the information hasn't changed, we can now multiply all through again by x prime x. Remember, this x prime y was here. I multiply that x prime y by x prime x to the power -1. So you have the reciprocal, okay, of x prime s multiplying everything. I'm multiplying everything again. It doesn't change the left-hand side, neither does it change the right-hand side. So when you come to the right-hand side, something interesting happens now. X prime x to the power -1, multiplying this one here, x prime x beta. And then finally, x prime x to the power -1 will multiply x prime epsilon. Now, x prime epsilon, okay, let me just show you something very good, because the last one is not shown, but we just indicated as 0. So you need to know how it became 0. So we're talking about x prime x to the power -1, and then x prime epsilon. Okay. So that's the last part that became 0. Why is that so? Okay, and watch why. Now, if you look at the prime, and then you look at the -1, the -1 applies to all the elements in the term. So the x prime will have a -1, okay, and then the x will also have a -1. And then you have what is outside here, the x prime, this one, which is x prime epsilon. So watch this, these two here, let me just indicate that with that. These two here, okay, you have one of them raised to -1, one of them raised to 1. So -1 plus, they are the exponents of the index x. So this thing is actually x to the power -1 plus 1, which is x to the power 0. Any number raised to the power 0 is 1. Sorry, any number raised to the power 0 is 1. Okay. And then you have the error term. And then the error term, you're going to take the expected value of the error term, which is 0. So it makes everything there 0. Okay. Now, so let's go to the next one, and you see this assumption. There are certain assumptions that will have to play a role, okay, for this to actually work. Once you get that, now look at the middle one here. Use a different color now to show. So when you look at this, what you are left with here, it is one of them is raised to the power -1. The other is raised to the power +1. So the two of them is raised to the power 0, which is 1. When you multiply that one by the beta, you get this data. Therefore, we can conclude based on this, because what you are left is on the left-hand side. Okay. Now, at this stage of this left-hand side, if I'm looking for the beta, which now becomes a cap, because I'm now estimating it. If I am looking for this beta, I can decide to even divide both sides. All right, I can decide to even divide both sides by, okay, or you can just see that they are already equal. Look at that. If the 0 should go away, let me just clean this one. If this 0 goes away, you are left with this beta, and you are left with just what is on the left-hand side. And therefore, if I turn it this way and then bring this one to this side, You are now left with what is here, which is x prime x to the power -1, and then x prime y. What is this? This is the coefficient of beta. So experience, its coefficient is maybe 20.
Yeah, hello.
That is beta. Okay. You have education. Okay, education has got a coefficient of 0.6. That is the beta estimated. And so if you have a data frame, and that data frame is organized nicely like this, you can drop all of this into the data frame, and the data frame will give you the score. This information is what we used to learn in undergraduate as that, okay? Where you have an x, and then you take the x to the power -1, and then you manipulate it and eventually get this beta parameter. Okay. That is the principle behind the ordinary least square. This is what we call the measurement, the line of best fit. So by the time you get that line of best fit, it has generated all of the OLS beta for each independent variable for you. And that is the first step, because remember, anytime you have a random variable, you define the random variable by not only the mean, which is what we use here, we use a mean approach, but not only the mean, but also the variance. The variance, which the square root of it is the standard deviation. So sometimes we describe any particular distribution or random variable by its mean and standard deviation, So now that we've been able to use this to find the mean of the beta or the beta, we should be able to use that same principle to also get the variance of beta. How do you get that? Okay, keep this in mind. So what we've done here, keep it in mind. So we are going to prove that the variance of beta cap, which is the beta that we've estimated right now, is variance. What are the deviation from this mean? The variance of this beta cap is equal to the expected value of the beta cap minus the true beta. So this is the actual beta, and this is a true beta. Yes, nothing.
Prof, I was following, but I think I got lost with how you calculated the mean for the previous slide. The calculation I got lost somewhere. Please, if you could go over that part again.
Okay. Now, to be honest with you, to go back, this one, I've done multiple videos on this. So you just have to take your time and go through it yourself. You will know. Okay. Sometimes to be able to fully get this, you have to go and learn matrices, learn exponents, learn, several things to be able to come with this. The key important thing after multiplying through with this, okay, the key important thing after multiplying through with this is using the assumption of expectation. The expected value of this error term. The expected value of this error term is 0. Okay. Now the expected value of all the matrices is themselves. The expected value of x is x. Okay. The expected value of x prime is x prime. Okay. So that is what changed the whole scenario from here. Okay. So the expected value of whatever you see, because this is where you take the expected value. Okay. The expected value from here, you take the expected value. The expected value of this becomes everything itself. The expected value of that here, this there, it becomes all of it itself. So it becomes the same thing. But the same thing, 1 is to the power 0. Sorry, 1 is to the power +1 here. This one is to the power +1. And this one is to the power -1. So -1 plus +1 is 0. And any number raised to that power 0 is 1. That 1 multiplying the beta gives you this beta. Already I've taken the expected value of this error term, which is 0. Okay. And so if I take the expected value of the beta, okay, one of the rules of regression is blue, okay, best linear unbiased estimator. So if you take the expected value of beta, okay, that should be beta cap. Okay. Again, I need to prove that, but you need to just check the papers. The expected value of beta, okay, cap is beta. Okay. So, or the expected value of beta is beta cap. So it is from that which you will now come and get this, which when you now rearrange, you get all of this information. But remember, these are matrices. So if you take them literally like letters as they stand, you will not be able to get, these are matrices. You are not just taking the transpose of things, you are taking the reciprocals of the transposes in things. So just take some bit of time and go through it, okay? And that will guide you. But keep this assumption in mind. The assumptions we went through, expected by, in fact, you even have to keep the homoscedasticity assumption in mind because we're about to use that pretty soon. Okay.
Okay, Prof, thank you.
Right, let me clear this. One of the things sometimes I sense is that sometimes you might get it all here. Sometimes you might not get all of it here. Don't worry, don't worry. Go sit down, get it. So let's prove that the variance of beta cap equals to sigma square x prime x to the power negative 1. Okay. This is the homoscedasticity. Now, this will generate the variance covariance matrix. What is the variance covariance matrix? Okay. The variance covariance matrix is what the entire regression information is based on. Because all the values you are looking for, you are generating are from this variance covariance matrix. And you can prove that the variance of the beta cap is equal to the variance covariance matrix. Remember this. This is what we just found some few minutes ago. The beta cap is x prime x to the power negative 1 x prime y. So we know this from the previous. Okay, keep that in mind. Okay. If I substitute for y, the value of y, what is the value of y? Let me just remind you. Y is given as x beta plus the error. So wherever I see this y, I can substitute this x beta plus error. And that is what you have here. Follow me. Once you've gotten this, done this substitution, because we are proving, okay? Remember that in this here, beta cap is equal to all of this. We can now expand this. Let me just go back for you to see. Okay. There are two parts to this formula that you are seeing here. What is the first part? The first part is that you can take these values and multiply it by that. And then you can still take this and multiply it by that. If you take it all and multiply it by the first one, you get x prime x to the power negative 1 x beta. Okay, then plus x prime x to the power negative 1 . Okay, let me just go back to the first one. I didn't finish because there was some of the right term that I left. So x prime x to the power negative 1 x prime before x beta plus you're taking the whole of this again. You get x prime x to the power negative 1 x prime and then epsilon. So that is what you are having here. Now watch this carefully. And when you watch this carefully, you will notice that this one is the same as this. The only thing is that one is to the power negative 1. And the other, which is not written, is to the power positive 1. And so the whole of this can cancel off because they become 1. Okay, and so here we'll be left with only the beta. And then here, we'll also have some few things left. So when you go to the next line, let me just clear this. When you go to the next row, okay, what I just said is what is here. So you can see that this was expansion, and then this one tend to stand on its own, and then we are left with the last part here. Now remember that the expected value of beta cap, because that's what you have in the formula here. Look at it. We are proving this. We are proving this. The expected value of beta cap. I need to know that first. Then I need to know beta. Okay, all of them prime. Then the expected value of beta cap minus beta. That one has no prime. The expected value of beta cap is given by the whole of this, which is what we have here. Okay, it's everything in this blue. Okay, that blue, this blue here, that is the same thing here. Okay, but the thing is that the expected value of this first one is itself, so that one is gone. What about the expected value of this? I told you earlier that the expected value of all of this is themselves. So the whole thing is just going to be the expected value of the error term. And we know that the expected value of this error term is 0. So it makes the whole of this thing what? 0. And that is why we are left eventually with this beta cap. So the expected value of beta cap is beta. Keep that in mind. Okay. So it means that if I have to find the expected value of this one, it is beta. And then I need to attach the prime to it. But this one has no prime. So we keep these two, keep this final one in mind, and then we move on with the proof. We're not going to substitute everything we had into this formula up here. Okay. And then we can now make some beautiful variance covariance matrix. So what is the variance of beta cap? What is the variance of beta cap? Because that variance of beta cap would lead to the generation of the variance covariance matrix. What is that? This is how you derive it. Okay, let's drop it all into the formula. Okay, so remember the formula I showed you was beta. I told you that the expected value of beta cap is beta. So now that we've proven that the expected value of beta cap is beta, we put the beta here. Okay, then plus the beta itself. But please remember the beta itself is here. Okay, this is the expected value of beta cap is beta. The beta itself is from that formula here. The beta cap, look at this beta cap. The beta cap without expectation. Okay, that is it. That is it in the blue one. So I'm going to substitute that blue one here. Okay, that's the beta cap. And then you have the beta. It has to be primed. And according to the formula, it's the same thing this time without prime. At this stage, we can take the expectation. How do you take the expectation? Well, watch it carefully. This beta has a prime, and this beta has no prime. Okay, this beta minus this beta will already kill themselves. Beta minus beta, gone. We are left with what is in the bracket. Let me use some colors too. So this is minus, and this is plus, gone. This is minus, and this is, sorry, this is plus, and that is minus, gone. But there's a prime with whatever is in the bracket, there's a prime there. So now we can take the expectation of that, which is what's left here, and then the expectation of that, which was left there. At this stage, it's just a matter of expectation and then prime. But remember, we are taking the expectation of all of them. So if I take this epsilon and this epsilon, and I decide to take their expectation, okay, I decide to take their expectation, I'm going to get something very beautiful. But we'll come back to that. But let's deal with what is in the bracket here. X prime x, -1, x prime, x prime x, -1, x prime. So technically, when you look at this, okay, this x prime x, okay, -1, this one here, that is the same thing there. So I can write it again, x prime x to the power -1 again. And I'm talking about this. Now, beside each one of them, you have x prime and then x prime. Okay, so beside each one of them, but this one, this x prime already has a prime here. So because it already has a prime here, it becomes x prime prime, and x prime prime is x. So what is in the bracket becomes x, and what is here becomes x prime. So I can rearrange them rather first. So I can say x prime, one is x prime, one is x. So I can say the first one should be x prime, the second one is x. And then I'm left with the epsilon prime. Okay, remember this epsilon has a prime. So you have epsilon prime, and then the second epsilon has no prime. So what I'm doing is that you're taking the expectation of it. When you take the expectation of this, you get the same thing. Now you can see that these two will cancel because one is positive, one is negative. We are left with the -1 here. And then these two, when you take the expectation of the epsilon, this one will give you an identity matrix. Okay. And so when you check it all, okay, you get this beautiful, this was a point I was saying, x prime x is the same as x. And when you go through this, by the principle, when you take the expectation of this, when you take the expectation of this is homoscedasticity assumption. And the homoscedasticity assumption is the constant variance assumption. Okay, so constant variance assumption, this is how you write it. This is homoscedasticity. When you rearrange all the things outside of it, you get this, you cancel, take some, you notice that this first part will go away because one is -1, one is +1. And eventually you go and get the variance of beta cap to be sigma square x prime x -1. That becomes your variance covariance matrix called errata demonstrating. So you've been able to prove that. Okay, so sometimes somebody might say, what's all this? What is that? That is like Hebrew. The whole thing is like Latin and Hebrew and Aramaic combined. But the thing is that in general, that's what the computer is doing. The computer is using the variance covariance matrix, to deliver the coefficient of the estimators. Okay. So this is a variance covariance matrix. So the variances are on the diagonals. They are the ones in the red here. And then the off diagonals are the covariances. Okay. And when you have this knowledge, you should be able to generate your beta coefficient for all this. So in conclusion, we know that the mean and the variance of beta cap is normally distributed, okay, where the beta cap becomes the beta, and then the other part is the homoscedasticity assumption, okay, which is from the which we call the variance of the beta cap. So this whole thing is the variance of the beta cap, while this is the mean of beta cap. Okay, so you should get a feel of this. Okay, what are they used for? The variances will tell you the variability or the spread of the data. The covariances will tell you the extent to which the elements are ordered, and then they move in the direction. They will all help you to do test of returns, test of hypothesis testing of the beta coefficient, F test of the overall, the R squared, adjusted R squared, everything that we are going to be doing, these things help you behind the scenes. Okay. The other usefulness of this is that you can calculate the standard errors of the estimators. And when we get to the table, you will see, okay, and the functions of the estimators. Sometimes when you are in logistic regression, you can create, this matrix for the estimated coefficient directly. They like using this table even to generate the scores. And then, oops. Can you hear me, please?
Yes, we can.
Yes, please.
Yeah.
This thing is a bit frozen. Okay. So when you get the parameter estimates and the variances, you can measure the goodness of it. All that I said, interpret coefficient in the model, okay, a test for the partial significance of the model, and several things that you can do from that. So someone might say that what is all of these mumbo jumbos? But the thing is that they are useful. Okay. And then based on that, you are able to get the beautiful results that you got. Okay, so that's it. Now, let's look at another thing before we go and use our data set. Okay, a quick information about dummy variable regression. What is a dummy? When you look at the word dummy, it sounds like something that is not moving, dummy, static. Okay, so a dummy variable is a categorical variable. Okay, it can have 2 or more levels. Okay, we said it multiple times. Okay, so let me just check your mind a little bit. If you have a dummy variable with 6 dummies, how many levels does it have? A dummy variable with 6 dummies, how many levels does it have?
7.
It has 7 levels. If the dummy variable has 8 levels, how many dummies does it have?
7.
Okay.
7.
If it has 19 levels, how many dummies does it have?
18.
Okay. I think that you've
No,
all
20.
No, your first answer was correct. Okay. I said if it has 19 levels, how many dummies does it have? And it has 18.
Okay.
18.
So you should know all about the dummy variables, okay? Because you will be able to interpret regression based on the dummy variables. And I'm going to do one particular example here for you. We'll come to proper interpretation, but I just want to crack this code quickly. This is a return on assets of a company made up of 500 plus 20 profit plus 30 type. That is a type of the company. Okay. And the type has been defined as 1 if the firm is domestic or 0 if the firm is foreign. How will you interpret the coefficient of profit? The coefficient of profit is 20. How will you interpret this 20? Who can tell me? How will you interpret 20? You have to interpret it with a mean mind, like regression mean mind. Okay. All right, Martin, tell us.
In the last condition, but let me still try. So what it means is that for every 1 CD increase in profits, return on assets will increase by 1%.
Okay. So some of the problems you face is when you start interpreting, regressions with percentages, when there are no logs, when there are no, percentages to be used. And that is why interpretation is very important. Okay. That is why interpretation is very important. And you are going to learn to master these things. Okay, so let me just quickly interpret profit for you. You have to start with on average. Okay. Why on average? Because this is an average information. You're just saying it's not complete. On average, you have to hold all the other factors constant. But I want to list the factors for a reason. So I will now say that on average, given the type of the firm, given the firm type and the size of the firm, a 1 unit increase, that 1 unit is nowhere in the information. A 1 unit increase in the profit of the firm. So I talk about the independent variable first. A 1 unit increase in the profit of the firm will increase the return on assets by 20 units. Will increase the return on assets by 20 units. Now watch, I didn't say will lead to a 20% increase in the return on assets. No, will lead to 70%, the dollar increase. No, I use the word unit, so that you keep the unit of measurement general. And I also said a 1 unit increase because profit can rise or fall. Okay? Profit can rise or fall. So 1 unit increase in the profit will raise the return on asset by 20. Why did I say we increase the return on asset? Why didn't I say we decrease? It's because of the plus. So the plus means that it will increase. It will increase what? The dependent variable by 20. But that interpretation is different when you are interpreting. That interpretation is different when you are interpreting a dummy variable like type. Because remember, type is a dummy, it's not increasing. So you can't say that a 1 unit increase in type. So how do you interpret it? Okay. Type, how do you interpret? This is how you're going to interpret the type. You will say that on average, given profit because profit is another variable there. Given the profit and the size of the firm, given the profit and the size of the firm, return on assets is predicted to be 30 units more. Return on asset is predicted to be 30 units more if the firm is domestic than foreign. If the firm is domestic than foreign. Why did I focus on domestic? Because the story told you that the type is 1 if the firm is domestic. So the one that is 1, that is what you are going to interpret in favor of. And this is a comparative interpretation. So it is domestic versus foreign. So once I speak about domestic, I'm also talking about foreign. That is why I said return on asset will be 30 units more. Why more? Because of plus in front of the 30. It will be 30 units more if the firm is domestic than foreign. But if the value, okay, so what this means is that if you are interpreting it in favor of foreign, you're going to say that on average, given profit and the size of the company, return on asset is predicted to be 30 units less if the firm is foreign than domestic. Okay, so you can interchange that, but you have to understand that it will be an opposite because the two are comparative. Interpretation is very important, and we'll come to that, when we come to the practical section. But I want you to know that you've got to learn how to interpret continuous variable and differentiate that from discrete variable because the interpretations are not the same. Okay. The last thing I want to talk about today has to do with the dummy creation. So sometimes you can get a data set, and the data set has got both dummy variables, categorical variables, and numerical variables. The numerical variables are ratio, you don't touch it, they are what they are. But the categorical variables, you want to create a dummy. If you put this into R will automatically create these things for you. Okay, you can run that. But sometimes you want to create it yourself and then use it in Excel for some other purpose. Well, you just have to count the number of levels and the location. If the levels are 2, like rural and urban, then you should know that you are going to create a dummy, which is 1. If you count the number of religions and the religion, and there are 3, Christian, Muslim, Buddhist, then you are going to form a dummy variable, which is 2. Okay, remember, the dummy variables are always 1 less than the number of levels. So once you create a dummy variable for location, let's call it LU, then wherever you see rural, you can put in 1 or 0. You choose which one you want. Okay, so here I decided to choose 0. So wherever you see rural, okay, the first one is 0, rural. Second one is 0, rural. Third one is 1, urban. Fourth is 1, urban. And the last one is rural. That's what you see here. I created 1 dummy. But for religion, because there are 3 levels, you create 2 dummies. So RC is religion Christian, RM is religion Muslim. And again, when you take the Christian one, anything that is not Christian will be coded as 0. Anything that is Christian will be coded as 1. Ladies and gentlemen, that is how you organize yourself. So when we are meeting next week, what's going to happen next time? What we're going to happen is that we are going to take the data set, the Burkutu Venture data set, and we're going to continue our article that we were publishing and use that to incorporate all that we've done in regression here. And then we'll look deeper, because we've not looked deeper, we'll look at all the diagnostics, all the interpretations, all the, the statistics used to determine the fitness, everything. We shall use them and look at all of them from that time. Remember to drink deep or taste not the Pierian spring. There shallow drought will intoxicate your brain, and drinking largely will sober you